Today, I'm going to just present one of our work we are currently working on, this RSI structure interaction analysis. Okay, let me start. First, I will introduce just a general concept of this RSI analysis first, and then this MIDAS software, how it works. I will explain you how to verify this software, compare with the UIC code. And we have one project which is ongoing, and so we are using this MIDAS software for this RSI analysis. And so I will just briefly explain how we are working on. And then finally, I'm going to just brief you what I found and what I learned during this RSI analysis in India, as per this India. I understand most of people they are working for this railway project today. I heard that from India Railway as well as Light, and so many consultants who is working on this rail structure they are here, and so I think most of them you know about this RSI analysis. This RSI analysis, if you have a railway bridge, if we have a rail above the bridge, and we have to consider this rail and structure interaction, because the rail is linked together with the bridge by some fastening system. And previously, I think in India, this CWR, which is a continuous welded rail, was not common, and so we use just a normal rail, which has always just this kind of joint in the middle. And nowadays, there's a metro and Hyderabad metro thing, and currently this project dedicated freight corridor. We are using this CWR, which is a continuous welded rail. The definition of this CWR is around more than 200 meters if this rail is continuous, because the phenomenon and behavior of this rail is different. So we call this as a CWR. And the advantage of this CWR, because we don't have this kind of, we can remove this kind of joint and rail, and so this joint always create a lot of this dynamic impact, as well as this will reduce the lifespan of this rail, and so currently there is a huge demand, and most of the projects nowadays we are using CWR. First of all, we need to understand this the impact of the effect of CWR, difference between the normal rail and the CWR. If this rail is continuously welded on ballast, and then if temperature goes up or goes down, and due to this temperature, we have some this kind of stress will be happening. And so, for example, if temperature goes up and this rail try to expand, but this displacement is fixed by this kind of fastener. And so, in the middle portion, from the end to end of this CWR, we will experience this kind of stress, some compression. In opposite manner, if temperature goes down, then we will have a huge tension in the rail. In addition to this, railway has to cross some bridge. And so underneath of this rail, if we have a structure, and this structure also shrink or expand due to temperature, and as well as because of this train loading, this girder itself will deflect as well as move, and because of this, some additional stress occurring in the CWR, as you can see here. And this is some diagram of this system. If we have a rail here, and this is linked by a fastener on the ballast embankment portion, and the bridge also is linked by fastener. Sometimes we put ballast, sometimes without ballast also we use. And if required, we can provide some expansion joint as well. We need to look at this fastener, this joint detail. This usually, this link is not fully fixed. This link longitudinally, if there is a movement, this rail fastener gives some resistance. If there is a longitudinal loading in forward direction, it gives some it allows some movement, but there will be some resistance from the fastener. And this nonlinear property we need to understand. For example, if this is the resistance of this fastener, and if rail and the deck, if there is a displacement, relative displacement up to a certain limit, and this resistance increase like this. In UIC code, we just suggested, UIC code suggested some bilinear curve to demonstrate this nonlinear behavior. So up to 2M, for example, if we have a ballast track and up to 2 mm, this will go, this resistance may go up to 25 or 50, something like that. After then, if there is a further relative displacement happening, and this will start slipping, and so there will be no further resistance from the ballast, from the fastener. So this is a phenomenon of this load distribution. If there is a tracking or braking longitudinal force, this force will be first, it will go through the rail, and this from the rail through the fastener, some portion of force will be transferred to the substructure. And if there is a temperature loading, and due to temperature, this girder shrink or expand, and because of that, also there will be some additional stress and additional force to the pier as well. And if there is a vertical loading also, this girder is not, doesn't have infinite stiffness, and so based on the stiffness, this will deflect, and this end of the deck will rotate, and because of this rotation, there will be some displacement. This kind of thing we need to first understand before starting the RSI analysis. And there is a vertical loading. As per UIC code, two type of this loading load model is suggested. This is one model is model 71, and another model is SW0 or SW2. And as for the UIC code, braking and acceleration, this force is clearly defined. This acceleration 33 kilonewton, and maximum force for this acceleration also is given in the code, and braking force also 20 kilonewton per track, and in case of this heavy loaded train, 35 kilonewton per meter. Also, dumbbell load is also it's given in the UIC code. If temperature change, and rail temperature and girder temperature, it doesn't mean it's always the same. And so this difference of temperature between deck and rail also should be considered. And this is a criteria we need to satisfy as per the UIC code. First, this additional stress due to thermal loading and the braking and traction together with the vertical load. The limit is 72 for compression. So compression stress limit is given 72 if this rail radius, horizontal radius curvature is less than 1500, and it reduces if this radius reduces. And tensile stress is somewhat higher than compression stress limit, and so it becomes 92 because of rail. We should there is more impact if compression comes because the rail is quite slender, and so there is a different limit, compression and tension like this. And another thing, longitudinal relative displacement in bridge deck. This bridge deck, if this one bridge, if we have a simple span of bridge, if this bridge moves too much, for example, more than 5 mm, and this joint part, this ballast will be deconsolidated. And so there will be some damage in the track system. So there is a limitation of this longitudinal relative displacement. Also, due to vertical loading also, as I explained in previous slide, due to the deck end rotation, if there is also excessive deformation, displacement between two deck, and if it is more than 8 mm, also there will be some damage in the track. So these three items is a major item we need to check during the RSI analysis. So this is so far this is a general concept for UIC code, and we can use any other software, but first of all we need to verify this software is enough and reliable, and whether this software well demonstrates this rail and structure interaction. So UIC code has given some model, test case, which code. And UIC code has given this kind of deck type, and their test result itself. And so based on this, we can select one of the model, and we can demonstrate this kind of just structure using one MIDAS. And so we have done this kind of just verification using by selecting these two models, 60-meter span length and loading one direction with this kind of stiffness and the E value and I value of this girder. And UIC code appendix. UIC code appendix has given some certain value, and we compare this loading. This is a temperature loading case. If we have a temperature, we are almost just getting almost similar result compared to UIC code. And this is a longitudinal loading case, train loading case. Also, we are getting almost negligible difference in terms of tolerance. And this is summary of UIC code. You can find out this this summary table from UIC code. And similar manner, I have checked this MIDAS civil, and this result is quite comparable. This is, so I'm quite confident this MIDAS result, which demonstrates this rail and structure interaction very well. So this is some project which I have done this kind of RSI analysis earlier and currently ongoing project. And upper one, I think most of the people know Hyderabad Metro is also metro. This is metro bridge, having this kind of curvature as well. And so horizontal curve is there. And so I demonstrated it all using MIDAS and this portion. And this is a current ongoing project which I'm handling. Let me introduce this dedicated freight corridor project, which we are also participating. This is India, and from Delhi to Mumbai, we are now currently constructing new railway dedicated freight corridor, and this is Western dedicated freight corridor, and this is the Eastern corridor. And total length 1,500 kilometer and 1,800 kilometer west, Eastern corridor. And I just compared the Indian Railway and the DFCC this loading. What is the difference? And so as you can see, DFCC this freight corridor loading itself is quite different compared with the Indian Railway standard loading. And X loading is 32.5 ton, and length of this train is quite long compared to Indian Railway. And this is just one of the examples which we are currently checking the rail stress and deformation, such a thing. And just a short span, less than 80 meter span, and beam and slab, just a precast beam and slab. And this also, this current project also we are applying 35 degree, plus minus 35 degree for bridge deck temperature variation. And vertical loading, also we are, this loading unit, we are following the bridge rule as per IRS code, which is specifying the loading, equivalent load intensity as per the span length. Braking load, as per IRS code, is given 25% X load for loco, and 13.4 for train load, which is just a gondola. Traction loading is given. I think most of you knows about this IRS code and train definition. We have a 5 combination, train combination, 63 ton 2 loco, and 52 2 loco, or something like that. This diagram shows the configuration of this train combination. This is a combination 1. In this case, we have a 31. This part is a wagon, and this is a loco. And usually, loco has a acceleration force somewhat high, much high, and whereas this wagon has no acceleration. And in terms of braking, as you can see this green line, this loco has somewhat higher intensity than this gondola part. Bridge rule has given this configuration, but however, bridge rule has specified only this point loading only, with this spacing. So I just back calculated, try to understand the equivalent loading if we consider this as a corresponding distance of this one loco and another loco, and I got this number like this. And this is a combination 2, train combination 2, combination 3. And so each combination has different intensity. And 5 combination. And this is a bridge rule appendix, 27 and 26. Bridge rule 27, what this table is given is based on each span length. They define this total loading, which will be loaded within 80 meters. Whatever this 5 combination comes, just worst case, they have considered this one. So I can say this is the loading condition for specific small 80 meters span length bridge. And also, according to the traction and the braking force, also based on this, it's calculated like this. For example, if it is 50 meters, 617 is the maximum tractive force, whereas 80 meters, 653, like that. I was not familiar with this table, but I studied this one. The basic basis of this table is if we have a 80 meter, whatever this 5 load combination, this axle combination comes, whatever gives the maximum case, this is a table, and so that engineer can easily take this number when they design this bridge. So this is a very useful table when you design the bridge rather than RSI. But however, because of this loading itself, this 5 load combination, which is quite complicated, and as I explained this UIC code, they have specified this 2 loading, and in terms of this braking and traction, they specified just a certain equivalent uniform loading. Whereas this bridge IRS code just specified this 5 very clear, just a load configuration. However, in terms of braking and traction, they specify 25% or 13.4% of this axle loading. We may apply this loading as of all point loading in braking and traction, but which may take a lot of effort from the engineer. And this is a criteria for which we are adopting. This is just I made this table compared with this UIC code. Compression limit is 60. And tension limit is 75, which is quite somewhat conservative side than UIC code. This value is given in this IRS addendum and corrigendum slip number 45, like this. And so we are following this value rather than UIC code. And other requirement is also same as the UIC code. And this is one model what we are doing. So using MIDAS civil, so we demonstrate two track left, one track and another track. And we have a bi-foundation substructure here, and whereas right side we have open foundation like this. And this is just a MIDAS snapshot. We can define this kind of bilinear, nonlinear material to demonstrate this fastener, which is showing here. And so this is this model, just a configuration. Rail and girder is linked together with this kind of just a nonlinear multilinear link property, and substructure is modeled accordingly. So substructure model is done like this. MIDAS is easy to add this substructure in RSI analysis also. And so as you can see here, substructure column part and the foundation, pile cap and the pile also it's all modeled like this. It made us easy to change this foundation if we have to change this foundation if we face any problem during the RSI analysis. And open foundation model also it's done like this. And loading, we need to apply this loading train to simulate. This train is traveling here, and so each load, we have to define a lot of different loading case, which we can use MIDAS, which is very useful to save our time. We need to apply both direction, forward direction as well as reverse direction. So basically, we check the temperature and braking and traction effect and vertical bending, and check the rail stress due to temperature, how much we are getting, and for braking, how much we are getting, and the vertical loading also how much. And this is one of the example temperature loading, because this temperature, if this rail, if this girder get 35 degree temperature rising case or temperature falling case, we can get this kind of rail stress. And so usually this peak stress comes to free end to the abutment. So we are getting around 16.4 MPa. And this, as you can see here, we have to check a lot of case after changing this train position. And due to vertical loading, if we have vertical loading, obviously, if this is a fixed end, and so fixed end part, we are getting higher tension. And if train moves and this force is slightly reduced, but other location where the pier location, because compared to this embankment part, this pier is somewhat flexible, and so we are getting less stress like this. And this is a summation of braking, and this is a case of braking and traction. Also, due to braking and traction, we have to check a lot of this loading position and made an envelope. This one. So this is another track, which is mainly this acceleration force is loaded part, track 2. And this is final rail stress checking, combining all temperature loading as well as vertical bending as well as braking and traction force, and we concluded this rail stress is within the limit. One more thing, we need to check this relative absolute horizontal displacement. This is abutment 2. Another side. So as you can see, this much displacement is happening at abutment 2, which where we have a free end, and also we concluded this movement is within the limit, and so we don't expect any deconsolidation of this ballast. And so this RSI analysis shows this structure is okay. This is ECPU. We checked due to vertical bending also. This limit is 8 mm, but we don't expect any such a significant problem because this girder itself, this span length is very short and the girder height is quite steep. And so this situation is normal. Just we concluded this end rotation with such a short span. With the current just a conventional structure in railway structure, this is not an issue. Mainly, we found this rail stress is critical. Yeah. And so we are currently undertaking lots of other structures, so RSI analysis using from our design team. And I'm going to share some finding what I have observed during this analysis. First, this substructure stiffness. Usually in conventional just a structural design, we don't need to consider this kind of this foundation rotation. I mean ground condition. Usually we just consider bottom of foundation is quite rigid, and so this will give always somewhat conservative value and safer side. And what I observed, because we are modeling this soil spring as well, so I would say this our analysis, we are doing this analysis considering this rail and structure as well as geotechnical just soil condition as well. In RSI analysis, this substructure, this stiffness is quite a significant factor, and so we need to look into this stiffness very well. First, just elastic deformation. If this column, if there is a horizontal force acting on top of the column, this will deflect. This will be based on this elastic deformation of concrete. And together with this, if this soil has some spring value, if it is ground condition, based on the ground condition, and we need to model this as some spring. And there could be there is a possibility of rotating this structure, even though this is within the stability limit. And there is another possibility of just a horizontal translation of this foundation also. So we need to consider all these three. And so based on this, we have just assessed what is the impact of this rotation, and based on different subgrade modulus of reaction, we check this one. And so for example, if we consider rock condition, which doesn't usually, we can ignore this foundation rotation, this will give just a 7 mm maximum deflection, whereas we may get almost 14 mm top displacement if we take just this kind of subgrade modulus of reaction. So during the design of this railway structure, especially if we have such a high, if we expect such a high longitudinal loading, braking, and traction, I would recommend just look at the foundation condition carefully. And this case, as I just explained when I explained about this train 5 combination, this is one of the combination, combination 1, which has a maximum traction force, acceleration force. And we can think about this traction force divided by this equivalent length, and which will give this much intensity, loading intensity. And also this, in terms of braking, as we can see from this green line, we can divide by this corresponding loading divided by this distance of this gondola. I'm getting around 16.0 kilonewton per meter. I have just done just to understand this the significant difference whether we can just use this, UDL loading or point loading. And so I have just checked focusing on this abutment 2 side, I have checked some detail. And so I applied all as a point loading in MIDAS, as well as I applied just a UDL. And so we are getting almost similar result, which is just comparable. And this is another case, just in case of braking also. Previous slide was showing the traction case. Traction case, okay, because anyway, traction case, even if we apply the high intensity of UDL or point loading, total loading remain almost same, it should be same. But in terms of braking, if we follow bridge rule, we will get, as per the bridge rule, we are getting 24 kilonewton per meter if we take from that table, bridge rule, table 27. Whereas, I don't expect such a high value for this gondola part. And even this maximum, this combination 5, this local, also if we divide by this corresponding length, also I'm getting just a less value in terms of braking. So 21, less than 21. But bridge rule concern, I understand, if we have such a short span here, when we had just a normal track, which is not CWR. If this loading is loaded on top of this 18 meter span small bridge, and so we have to take this full force is transferred to the substructure. So that was the intention of bridge rule this table, not for the RSI analysis of this CWR case. And this is a point loading case as per actual train this configuration. And this is a uniform loading case. I concluded this result almost same. And then this is another result as per this bridge rule, which is quite high intensity. If we apply this whole loading, and I'm getting almost 4.6 MPa, somewhat higher side, this stress. So in terms of braking, my conclusion is just adopting this bridge rule, Appendix 27, may result somewhat conservative result. Somehow, it's not that much significant, just 5 MPa, something like that. But as long as it's also allowable stress limit is reduced from 75 to 60, so this is almost 10% compared to this is almost almost 10% of this allowable limit, which we currently are using. So my final finding on this one. Currently, this India, a lot of this railway structure as well as metro structure is coming. CWR, this railway RSI analysis is a hot issue in India, and everywhere all the consultants I know, they are now just working on this RSI project. And substructure stiffness, as I briefed you, we have to, because it was not an issue when we do some conventional, just normal rail, not CWR, when we just design the structure foundation, isolated stability, such a thing. But now we have to look at this substructure stiffness also, especially rotation. And finally, this load model, I think it's I would say quite clear in IRS code, but it's unclear how to apply this braking and traction force in RSI analysis. It's very clear 25% of local and 13.4% of this gondola. But I think it is good if we just specify this kind of loading, how to apply in RSI analysis, almost something like a UIC code, which will save a lot of time for the engineer. And I think most of the engineer understand this RSI analysis, even though RSI wizard, MIDAS provide excellent RSI wizard. And so to apply this kind of loading for 5 load combination take a lot of effort. And so sometimes I think we have to discuss openly and how to apply this, how to define this UDL, equivalent to UDL loading in RSI analysis in IRS code. So, and same thing, just simply adopting this bridge rule, this table in RSI analysis, I feel it will result, it may result some conservative side. Yeah, anyway, this is conservative side, and so it's okay. And actually, my intention of this presentation was one day I'd like to open discuss with all people who is working on this railway structure in India, and to make some guideline how to apply this train loading in this DFCC loading, or in either Indian Rail as well. That all engineers, it will be very clear, and we will keep some consistency, because there are lots of projects ongoing, and so this project they are applying this manner, and other project they are applying some different manner, which is, I feel, it does make sense. Okay. Okay. Yeah.